All right, we're going to take a look at lesson 4 in the second booklet for this unit. We're going to look at scale diagrams today. Scale can be represented in a bunch of different ways. We can see that scale can be represented through words as ratios, fractions, or in diagrams. So for example, an enlargement by a factor of 10, if we were going to blow something up by a factor of 10, and we were going to write this in a ratio, we would see that it would be written as 10 to 1. Okay? If we were going to write this out in words, we might say something like 10 millimeters on the drawing represents 1 millimeter on the actual object. We could represent it as a fraction, or we can also represent it as a diagram. And maybe you've seen this kind of diagram on the bottom of a map or something like that. The really key thing to keep in mind when it comes to this scale factor is I want you to notice where the 10 goes relative to the 1. Okay, so the 10 in our ratio is the new object. The new object is something that was 1 unit before is now going to be 10 units. Okay, with words it's a little bit easier to see where what's new. In a fraction, we put the 10 on top. The 10 represents the new size, right? The new object, and the 1 comes from the original object. And in the diagram, again, the diagram would probably have a little bit more context. It would be a map, and it would make a lot more sense kind of looking at it on a map, right? We can see that 1 millimeter, this space here isn't 1 millimeter, right? It's 10 millimeters, but it represents 1 millimeter here. So the 10 is kind of implied in the diagram. We're not going to worry about using diagrams too much. It will pop up, but most of the time what we're going to see is we're going to do ratios and fractions. Okay, the scale factor, so this factor that we are expanding or like enlarging or reducing dimensions by, we're going to call that K. Okay, that's a big idea in this unit. We are going to spend pretty much the rest of the unit looking at K, right? And K is that factor that compares the measurement of a shape in the diagram to the measurement of the actual object. And again, it expresses it either as a ratio or fraction or words or etc. You'll see this kind of fraction set up here, this equation where K is equal to the diagram measurement over the actual measurement. I personally don't like that. I always find it somewhat confusing to kind of determine which one's a diagram and which one's actual. Like that doesn't seem to have enough context to me. So I always think of K as being new over original. It's the ratio of the new thing over the original thing. So it could be the length of a dimension with an enlargement over the original guy. So I like new over original better, and that's what I'm going to use as we kind of work through these problems. Hopefully what makes sense now when you think about it, if the new thing is bigger than the original thing, the new dimensions of the new guy are bigger than the original guy, then we'll get a number bigger than 1 here, right? So that's an enlargement. So when K is bigger than 1, we'll get an enlargement. However, if the dimensions of the new thing are smaller than the original thing, then K will be between 0 and 1. It's a fraction or a decimal, and we're looking at a reduction of the original shape. All right, so what I really hope you get out of the next couple of lessons is how to calculate K. That's the big concept here. That's kind of what's going to carry through to next year. Not necessarily the K calculations, but the concept behind it is what's going to carry through to the stuff we need to do next year. Okay, so how we're going to deal with K right now is just look at some scale drawings. And I think you would have done these in grade 9. I have a feeling that this is, again, part of the grade 9 curriculum, but it's in ours as well. It's really going to lead to design and measurement questions next year. So, and these are kind of fun. They're not too tricky. So here's an example. We are given a diagram of a little house here, right? Or a square with a circle and a triangle roof. The question says, enlarge it according to the scale 2 to 1. So this word enlarge is very nice. It's telling you that you're going to have to make the picture, the new picture, 2 times bigger than the original. Now, that's extra nice because you're not always going to get that context. Quite often you're just going to get a question that says, draw the shape, again, with a scale of whatever. Okay, so we need to be able to read this part right here. We need to know what this 2 to 1 means. Okay, and we're given this clue enlarge, but we're not always going to be given that clue. So what does this 2 to 1 mean? Well, if we go back up to the notes at the top of our page, right, that 2 kind of sits in the same place that the 10 did at the top here, right? Where that 2 is the new shape. Okay, and the 1 is the original. Okay, so the new shape has to be 2 times bigger than the original shape. For every 1 square that the original shape takes, the new shape is going to take 2 squares. Okay, so that's it. We just got to draw it. And because this isn't very complicated and you've probably done this before in other classes, the expectation is that you are very careful and draw these out using as many different sides of the shape as you possibly can. All right, so let's take a look at this square here. It's got a length of 4. Obviously, then it has a width of 4. So for every 1 square in the original, our new shape is going to have 2 squares. It's going to take up 2 squares. So this length of 4 is going to get translated into a length of 8. Okay, so let's just start down here. 2, 4, 6, 8. Did I do that right? 2, 4, 6, 8. There we go. And then we're going to go up 2, 4, 6, 8. And the square then looks like that. I don't know that I have a thicker pen. I'll look for one. Maybe I'll find a brighter color here so we can see what's going on a little bit better. Maybe I'll try a brighter kind of purple. Hopefully it'll stand up a little bit better. All right, so that's the square. If I look at my triangle has a height of 3. So on my new picture, it's going to have a height of 6. So 1, 2, 3, 4, 5, 6. Okay. Yeah, that's halfway between the length of my square. So I'm going to carefully try to draw a triangle. So this triangle has dimensions that are 2 times bigger than that triangle. And then we need to look at our circle here. So our circle is 1 unit away from each edge inside this square. So I kind of marked it out, and now it's probably not going to be a very pretty circle, but no, it's a terrible circle. But it's at least it's pretty good in proportion. If not, that is our scale drawing. You don't have a lot of practice for this in the independent practice. So what I'd like you to do is I'd like you to pause the video, and I'd like you to kind of take a look at this question here. Try it out on your own. Okay, so like really actually pause the video, actually try out this problem on your own. And when you unpause it, your work should look something like this. Okay, this scale is 1 to 1.5. So 1 is our new shape and 1.5 is our original shape. Okay, so that means our original shape is bigger than the new shape. Okay, a couple ways to think about this. If you don't like the decimals, you can just multiply kind of both sides of this ratio by 2 to get rid of the decimal place. If we double both sides, it means for every 2 squares the new one takes up, that represents 3 squares in the original. So you could think that 3 squares shrinks down to 2 squares in the new picture. Okay. Also too, when we calculate k using this scale here, k is going to be our new divided by original, and when we put 1 divided by 1.5 in our calculator, we get 2/3. We get the fraction 2/3. So the new picture is 2/3 the size of the original picture. And you can see that our 9 spaces, that's the width of this rectangle, gets reduced down to 6 because that's 2/3 of 9. 6 spaces gets reduced down to 4 because that's 2/3. 2/3 of 6. 3 spaces. 3 spaces here, and the base of our triangle gets reduced down to 2. Okay, you have to do a little bit of kind of estimating to get the height of this triangle here, but that should work out for you. Okay, so hopefully your picture looks something like mine. Maybe you drew your circles a little bit better too. Okay, let's go back and take a look at the last problem in this particular lesson, and how, like what most of our questions are actually going to kind of ultimately look like. So the question is, the height of the Eiffel Tower is 320 meters. The height of a scale model of the Eiffel Tower is 8 centimeters. Determine the scale factor of the scale model. So whenever you're asked for scale factor, this is asking you, what's K? All right. We have another kind of thing we need to consider in this problem. The real Eiffel Tower is 320 meters, but the scale model is 8 centimeters. So we need to change either this guy to centimeters or this guy to meters. And it kind of doesn't matter which one you do. I'm just going to make this guy into centimeters because then there's no decimals in my work. Okay, so we're going to just kind of remind ourselves that 320 meters equals 320 times 100, which is 32,000 centimeters. So really important thing to note is, unlike rates, scale must have the same unit. Okay, so when we were talking about rates in the last part of this unit, we were saying that we were comparing 2 totally different units to each other, and that was kind of the point of rates. When we were talking about scale, however, we have to have everything represented in the same unit. Okay, and ultimately our K factor has no units attached to it because the units cancel off. All right, so how do we find this K business? Well, I like to say K equals new over original. Okay, I find it way easier to think about it like that. Our new thing is the scale model, right? The little guy. So it's 8 centimeters tall. Our original is 32,000 centimeters. Notice our units cancel. Okay, and if you put this in your calculator, if your calculator is kind of set to fraction mode, you will get a fraction. Okay, and k can be written as a fraction. K can also be written as a decimal. And that might be what you get in your calculator when you do 8 divided by 32,000. Okay, now let's think about it. Does this scale factor make sense? It's a very small number between 0 and 1. And back in our notes, back up here, when the scale factor is between 0 and 1, the new shape will be a reduction of the original shape. So this k factor here is definitely between 0 and 1. It's a very small number, and it represents a reduction. An 8 centimeter Eiffel Tower scale model is very, very small compared to the real Eiffel Tower. So this k factor makes sense. All right, hope that makes sense. Try some independent practice.